I've witnessed quantum go from a twinkle in our eye to a full-scale national initiative.
So these are things which boggle the mind at our level, are just how the quantum world works.
Excitement breeds ideas, and it also breeds the ability to do something different and new.
Hello, everyone, and welcome to The Sound of Science,
the podcast highlighting the voices behind the breakthroughs at Oak Ridge National Laboratory.
We're your hosts, Jenny Woodbury
and Morgan McCorkle.
Quantum mechanics. Does the term alone make your brain hurt a little?
If so, you're not alone. It's a very complex branch of physics where things are just kind of weird.
In our everyday lives, we're much more familiar with the laws of classical physics, which explain the behavior of energy and matter on a scale that we can observe with our own eyes.
These laws address concepts like motion, force, electromagnetism, and gravity. While the math behind them can be complicated, these basic ideas are pretty intuitive.
For example, I know what goes up must come down because I can toss a ball into the air and watch it fall to the ground. That's just how gravity works.
However, when you start examining matter and energy at a much smaller scale, things get trickier.
Scientists begin realizing this when they try to apply conventional physics rules to individual atoms and electrons.
They found subatomic particles didn't behave classically at all. Their behavior was all over the map.
When you're a child, when you're a really small kid, what do? You pick up a spoon and you look at it and you drop it. And you do that repeatedly. And your parents look at you and say, quit doing that. But what you're doing is an experiment. You're trying to understand reality. So you keep dropping that spoon and eventually you say, okay, things drop to the floor. You get a little older and you think the entire world is this world in which we live. I throw things at the wall, they bounce back. Everything's kind of classical. And then about 100 years ago, people started throwing little things at a wall, electrons. And what they found is that the electrons can penetrate right through the wall. They found that light can act like a wave, not just a particle. And it can act like a particle if you do the experiment the right way. So it has this dual characteristic. Classical equations have light as a wave, but the experiments tell you it's also a particle at the same time. That's where the origin of the word quantum, one little thing, came from.
That's David Dean. He's a physicist at Oak Ridge National Laboratory.
In the quantum world, a particle can be two things at once. And if you think that sounds a little mind-blowing, you're in good company.
One of the guys who invented quantum mechanics, his name was Niels Bohr. He said, if you think you understand quantum mechanics, you don't understand it. And I think that is still kind of a true statement. I've done quantum many-body theory my entire professional career. And there are still things that kind of like bother me about the type of stuff we do. You can simplify it down and say, well, it's just interactions of particles and they move around and they talk to each other in a particular way. But at the same time, some of these things and some of the experimental results that you see kind of give you pause.
While quantum mechanics may be harder to relate to than classical physics, the principles apply more to your daily life than you think, especially when it comes to technology.
And you're affected by it every day. You just don't know it. You don't think about it. Every single day, you pick up your iPhone and you play with the screen, right? You mess around and move your finger back and forth and the screen works and everybody's happy. Well, that's actually a quantum mechanical effect because people have come in and figured out how to make the surface on the screen, able to listen to your finger.
The strange behavior particles exhibit at the subatomic scale has the potential to create a technological revolution in computing, materials, networking, and sensing.
To harness this power, the U.S. Department of Energy has established a suite of quantum information science research centers at 5 of its national laboratories.
ORNL is home to the Quantum Science Center, which brings together national laboratories, academia, and private industry with the aim of advancing quantum technologies.
We talked to several researchers at ORNL to understand what they hope to accomplish. You just heard from David Dean, the center's director. Next up is Travis Humble, a quantum computer scientist who serves as the center's deputy director.
The Quantum Science Center is a new DOE research center that's focused on the science of quantum information. This is a topic that lies at the intersection of information and quantum physics, and it's an exciting area where we expect to see lots of new discoveries and developments for technology. The purpose of the Quantum Science Center is to address the key roadblocks in the development of those technologies, and especially to look at how they can impact U.S. economic competitiveness.
Quantum computing is one of the technologies the center is looking to advance.
We've seen decades of advances in the development of computers, mainly powered by the idea of Moore's law, which is that transistors can continue to get smaller and we can continue to get more power and performance out of them. But eventually Moore's law runs into the atomic limit. And at that scale, quantum physics takes over. Well, quantum information science is intended to understand how to use individual atoms and molecules to perform computation. And so there's an exciting area there where we actually could build quantum computers out of individual atoms and then far exceed the types of performance that we see in today's high-performance computing systems.
The Quantum Information Science Center isn't looking to build a quantum computer. One of its goals is to research and develop better quantum materials, which are key to enabling quantum computing.
So just what makes a material quantum?
To get a better idea of this, we talked to Stephen Jesse, a materials scientist at ORNL.
Early on, a lot of people were asking, what on earth does that mean? Because in truth, quantum mechanics and quantum physics governs everything that we interact with. And so why is not every material considered a quantum material? And really the defining thing is most materials, by the time they get to the size where we interact with them, all that quantum weirdness has been washed out and averaged out. And so when we think of, matter, when we think of two tennis balls, they're separate. They don't somehow magically morph together, or they don't know what each one is doing. But when you're talking about things, atoms and photons, which are elementary components of energy and elementary components of matter, things operate quite differently.
It's this different, or really just bizarre behavior that sets quantum materials apart from regular materials.
You can get superposition, which means that a state isn't necessarily one thing or another. It can be something in between. And you can get entanglement, which means that two particles, even though they're separated in space, they are entangled in some way that they know exactly what each other is doing. So these are things which boggle the mind at our level, are just how the quantum world works. What separates a quantum material from a regular material is that some of these quantum properties actually are maintained to the macro scale, or it's something that we can observe even when they're large. And so it's preserving that quantumness at larger scales that we can observe is what makes them somewhat special.
However, maintaining these quantum characteristics at a larger scale can be challenging, as some of these materials can only hold their quantum properties for so long. This idea of how long a quantum state can exist is called coherence.
Scientists are looking for ways to lengthen coherence, so these materials can be used in various quantum technologies.
The lab has had a long history in studying, for instance, superconducting materials. And these are special in that the electrons interact in such a way that they give zero resistance when you try to pass current through them. Now, when you build up that kind of expertise here, both in growing materials, studying materials, and doing theory on these types of materials, that gives you the base to start studying other quantum materials as well.
The Quantum Science Center is targeting a new class of materials that might fit the bill: topological materials.
And what's special about this class of materials is that typically you have a block of copper. It's a conductor, and the outside is conducting, the inside is conducting, the whole thing's a conductor. Or you've got a block of glass, the whole thing's an insulator, the surface is an insulator, the bulk is an insulator. What's interesting about some of these topological materials is that you can get a very different property at the surface or at an edge that doesn't exist inside the material itself. A topological insulator is one example of this class of material, where the inside is insulating, but only the surface is conducting. And because of that, you get interesting properties just because the conduction layer is in a very thin layer. But what that also provides you is a very robust conductor, because it doesn't matter what the geometry is. The surface is always a surface.
In theory, topological materials offer the ability to host longer-lasting quantum properties and states. Manipulating particles along the edges and surfaces of these special materials might open up new ways of performing quantum computing.
They possess their quantum properties at the small scale, but those tend to be very fragile. And so if you want to use those for computing, you need to figure out a way to make them more stable. And topological insulators, if you can get those quantum states to live on edges and on surfaces, then it makes them much more robust. And so that's why, as a lab, we've decided to target classes of materials, because we've got the expertise in the synthesis, theory, and analysis of these materials. And we've got the quantum information sciences expertise on how we could potentially use these materials as well. And so with that combination, we think that we can use this robustness of these edge states to actually use these to do computation in the future.
Since quantum states are so fickle, special conditions are required to preserve them. One way to do that is to make them cold. And by cold, I mean really cold. Like colder than outer space.
To achieve these icy conditions, you need something called a dilution refrigerator. This isn't any ordinary refrigerator, though. It looks something like an upside-down wedding cake, with tiers of gold-plated copper rings, descending from large to small.
If you've ever seen a photo of a quantum computer, you've probably thought this golden structure was the computer itself, but it's simply the cooling mechanism for the computer chips.
It gets down to 10 millikelvin, and a Kelvin, as it relates to Fahrenheit, if you were at 0 Kelvin, you would be at negative 459.67 Fahrenheit.
That's Claire Marvini. She's a postdoc at ORNL and works in the Quantum Materials Laboratory, which houses 2 dilution refrigerators.
So we want to work at such cold temperatures for a couple different reasons, depending on what materials you're studying. If you're working with a superconductor, superconductors are what we conventionally use in a quantum computer. You have to be below that transition temperature where your conductor turns into a superconductor. And not only that, you want to work below these thermal vibrations and the thermal energy of the system. So we work in the sub 100 millikelvin range because we want to be below where these thermal vibrations are interacting with the system. So we're trying to freeze out everything that would disrupt the coherence of our system.
Claire's research focuses on testing materials for use in quantum bits, or qubits, which are the foundation of a quantum computer.
We're always working to improve coherence times in any qubit system. So right now, superconducting qubits are used in our quantum computers, but we're looking at other materials too that might have additional benefits.
ORNL is home to Summit, the nation's fastest supercomputer. At 200 petaflops, Summit is capable of solving 200,000 quadrillion calculations per second.
A computer with this kind of power occupies a pretty large footprint. The cabinets that make up Summit could fill 2 tennis courts.
There's no doubt Summit is incredibly impressive, but imagine a computer not only exponentially faster, but a fraction of the size and much more energy efficient. A quantum computer promises just that.
We're used to technology getting faster and smaller, but a quantum computer isn't just an upgrade to the computers we're used to.
Quantum computers offer a completely different style of computing altogether.
People are familiar with computers. They use them in their everyday lives, and computers are based on storing and manipulating information using what's called bits, which are a 0 or 1. You can think of it maybe as a coin on a table, heads and tails. Of course, this is very powerful. We can do many things with it. But nature actually allows us to store and process information in another way using the laws of quantum mechanics. And quantum mechanics usually describes how atoms and nuclei, very small physical systems, work.
John Martinez is a physics professor at the University of California, Santa Barbara. He's been studying quantum computing for decades.
But what was realized, let's say in the early 1980s, was that you could use quantum mechanics to store and manipulate information in a way that's much more powerful for certain problems than what we can do now with regular computers. And it's all based on the fact that in quantum mechanics, you have something called a superposition state. And if you generalize quantum mechanics to information, which is possible to do, this kind of superposition can be applied to a bit, 0 or 1. So you can encode a certain quantum state as a 0 and another quantum state as a 1, and then nature allows you to be in 0 and 1 at the same time.
The superposition state is what allows a quantum computer to process information exponentially faster than a classical computer.
You may be wondering just how much faster. Well, last year, a team from Google, NASA, and ORNL conducted an experiment to compare the performance of Google's Sycamore quantum computer and ORNL's Summit, which at the time was ranked as the world's most powerful computer.
Both Martinez, who was a senior scientist at Google at the time, and Travis Humble were part of that team.
We finally found a problem that a quantum computer, one of today's quantum computers, could solve much more efficiently, much more quickly, and using much less energy than even the world's fastest supercomputer, the Summit computing system at Oak Ridge, was possible of doing. And what was remarkable about this is that the difference between these two calculations, the quantum calculation using the Google processor and the conventional calculation using the Summit supercomputer, was not a small margin. It was a very significant days, if not years, difference in the amount of time it would take for these calculations.
Just how significant might be a little surprising.
We ran our quantum computer for about 200 seconds to take a million data points running the quantum computer. And to check if the quantum computer actually gave us the right answer would have taken, in the hardest case we did, about 10,000 years on a classical computer to run on it, something like Summit here. And of course, at 10,000 years, we can't check it. So what we did is we made an easier case, let's say fewer qubits, where we were able to check it. And then we kind of know how the runtime scales with this.
Sycamore was not only faster than Summit, but it was also approximately 10 million times more energy efficient.
So, if quantum computers are superior to classical computers, does this mean we may no longer need machines like Summit in the future?
Well, not so fast. Quantum computers have limits. One of those being something we've already discussed, the lack of viable materials for scalable quantum systems. But materials aside, there are still problems classical computers will need to be around to solve. Here's Travis Humble again.
Conventional computers are based largely on the idea of classical logic, the Boolean and or statements that we all sort of learn as puzzles early on. But quantum physics itself actually extends beyond that, and it uses properties of the universe that are non-intuitive and give us more tools to develop the different types of computing systems. So fundamentally, the difference between conventional and quantum computers comes down to the way that they process information. Now, of course, some problems are naturally tailored toward conventional Boolean computing systems, and we're always going to need those types of computers. But there are other problems, especially in scientific discovery, where quantum computers can provide performance enhancements that we would never be able to get with conventional approaches. So I see the future needing both types of computing systems, most likely working together.
While quantum computers won't render classical computers obsolete, the results of the Google demonstration hint at what's possible with future quantum computing systems.
While this particular problem was an example of a diagnostic calculation, it gives an indication of the type of differences we can expect quantum computing to bring. If I had access to the future quantum computer systems that we're trying to build today, I could immediately begin to address problems related to energy security, the development of new vaccines, food security, so many other areas that we already recognize the significance of computing, and quantum computers could only add on to that.
It's going to be a while before quantum computers are as prevalent as classical computers. However, thanks to a program established by the Department of Energy, scientists are being able to gain access to some of the world's existing commercial quantum computers.
The development of quantum computing technologies is very new. We're breaking new ground every day, learning something different. And in order to accelerate that development, the Department of Energy has established a quantum computing user program. We call it QC-UP. And it's run through the Oak Ridge Leadership Computing Facility. And the purpose of that program is to enable the world's best scientists to get access to quantum computers. And these are generally commercial quantum computers from vendors like IBM, D-Wave, or Getty, where based on proposals that the users write and are evaluated, they get access to these devices in order to test out their ideas and to evaluate what is really possible. So the Quantum Computing User Program is playing an important role as national infrastructure for our scientific community, but it's also giving us accelerated ways to discover what's actually possible using quantum computers.
The realm of quantum mechanics is as fascinating as it is mind-bending.
And we've really only touched on a fraction of what the scientists at Oak Ridge are currently tackling through the Quantum Science Center.
But the bottom line is that it's an exciting time to be in the field, and Travis Humble and David Dean couldn't agree more.
Over the last decade, I've witnessed quantum go from, a twinkle in our eye of hope that maybe this is something that we could do, to a full-scale national initiative, where the national laboratories, including Oak Ridge through the Quantum Science Center, are now leading that initiative to make fundamental change in the technology base of not just the United States, but the entire world. And that is such a dramatic change in 10 years' time. To go from, I hope someone will take me seriously, to listening to leaders of the world say, this is exactly where we need to invest our resources and train our people. So it's an amazing time to be involved with the Quantum Science Center and to work with so many people at so many different institutions on these goals that we think are really going to change that.
Oak Ridge has a lot of really smart people running around. Scientists, what makes a national lab? Scientists, facilities, and programs, right? And those people, a lot of them are really excited about this area. Excitement breeds ideas, and it also breeds the ability to do something different and new. And I think that's what this quantum information science area, quantum materials area, quantum computing area really does, is ginned up a lot of excitement. And so, my purpose in life at this moment in time is to make sure we capitalize on that excitement, have a center at Oak Ridge, and make sure it's the best center it can be.
Thank you for listening to this episode of The Sound of Science.
If you liked what you just heard, there's more coming your way soon.
We're launching a shorter version of the podcast called Soundbites of the Sound of Science, and our first installment will be on quantum security for the grid.
So make sure to subscribe so you won't miss a full episode or soundbite.
Until next time.